Welcome everybody to the first lecture of our machine learning course. My name is Tim Landgraf. I'm professor of computer science at Freie University, Berlin. And I'm going to do this with three of my students, Max, Luis, and David. Max will help us with making and grading the assignments, and Luis and David are helping me with slides and the lectures. So the course will, as you may have expected, happen mostly online. We will publish these kinds of videos for each lecture and also the assignments every Monday. And also we have a 10 a.m. session and a 2 p.m. session in which we answer your questions. So what you have to do really is to watch last week's lecture video and then come in the Monday morning session to ask your questions, and also understand and read the assignments of last week, so we can talk about this every Monday. And then after this Monday, you can go ahead and watch the current video and read the current assignments and use the 6 remaining days until Monday to actually solve and work on last week's assignment. So throughout this semester, we will look at different machine learning algorithms, and I've divided this into two big blocks. The first block covering the more classical machine learning algorithms, and then the second block will cover modern deep learning, so everything that's related and based on neural networks will start in January next year. And the first block starts today with an introduction. And note that both of these blocks are concluded with an exam, so there will be a midterm exam towards Christmas, and then a final exam towards the end of the semester. So in the course, we will look at different algorithms that you probably will either find in one of these books or in papers that we will then, of course, cite on the respective slides. Many of these books are available online, so go ahead and download them and have a look in them. For each part of the lecture, you will find a very good chapter in one of these books. So let's start with a definition of machine learning. As you may know already, machine learning is a field within artificial intelligence. Here in machine learning, we do subsymbolic processing of data. We learn models and do pretty much what could be also called statistics. We do, however, most of the time, no reasoning or causal inference, although there are a couple of algorithms available based on neural networks that actually do that. But commonly we would put this outside of machine learning. Deep learning now, in the last decade or so, grew as a field much bigger than this ellipse here in the slide would kind of make you think, but this really is only a subset of algorithms within machine learning and obviously within artificial intelligence. So let's, just to give you a notion of what machine learning is and what problems we want to tackle with machine learning, let's give you a couple of examples. So first of all, let's look at the upper left figure here. In some of those tasks, tackled with machine learning, our question is, okay, given a certain data set that describes a system's behavior over time, predict the system's behavior in the future. So this could be weather, this could be like in this photo here, the number of page views over time. Yeah, so this could be really a really hard problem because the history of data doesn't necessarily give you all information for the future. And yeah, so the second picture here corresponds to a Kaggle challenge. So those of you who don't know Kaggle are invited to visit this webpage. Here the task is given a review of a wine, classify this into the actual brand and into the actual I don't even know how to call that, the bottle, yeah, and the name of the wine. And also very well-known examples are ImageNet and MNIST, so data sets that show different objects. So MNIST is very simple, handwritten digits. It's a classical example in machine learning. So if you want to start, programming classifiers, you probably see this in the very beginning, and then the tasks make it harder. For example, classify one of each of these images into one of 1,000 categories. So, from, I don't know, maybe a leopard or panda bear to, guitar playing. So in the previous slide, we had high dimensional data, and then the output of the machine learning model is pretty low dimensional, right? So, the class of an image versus the number of pixels in an image, you really go down in dimensionality. Of course, machine learning can work the other way around, for example, by generating samples. For example, here in this figure, you see raw speech, raw audio of someone talking. This can be generated by learning models of real audio models of real audio recordings, and that works, of course, in different domains as well. So each of these people here aren't real people; they have been generated using something that we call GAN, generative adversarial network, and specifically StyleGAN2 that you can find on this in this publication here. And the people behind this person does not exist.com have implemented the model, and you can generate as many faces and persons as you like. So in machine learning, we usually discriminate between at least two subfields, supervised and unsupervised learning. And in supervised learning, we have a data set that consists of the input data. X, capital X, is a set of m-dimensional vectors, n many. And each of these vectors is associated to a label, also a vector, now in k dimensions. And these labels represent the output that our model is supposed to estimate. Yeah? So from the input data X and the labels Y, in supervised learning, the task for the model is to learn this mapping such that the error, the mistakes that the model does are minimized. In unsupervised learning, we do not have such labels. We just have the input data. And the task now is to find structure in the data, to learn representations that are somehow meaningful or useful for future tasks. So structure here in the data could be anything, but maybe start by thinking of clusters. So you have a couple of images that all show dogs, and then you have a second set of images that all show cats, but you don't. So they're intermixed, right? So that you don't know which one is dogs and which one is cats. But I mean, how would you as humans do that? Well, you look for features that dogs have and cats not, or vice versa, and then you can group those um, subsets into cluster one and cluster two. Yeah, and that's clustering. Yeah, we'll come to this in one of the later lectures as well. You can, of course, combine unsupervised and supervised learning into something that's called semi-supervised learning. But this is just one of the many flavors you can think of. There's a third subfield in machine learning um, called reinforcement learning. That's typically related to problems in which you have an agent that somehow interacts with its environment, and from the observation of the environment gets either a reward or a punishment for whatever um, action it has performed. And of course, it can observe how the world, how the environment changed. So one of the classical examples here is this card that's supposed to reach this goal here, but it doesn't have enough power to just go. Yeah? It has to kind of go back to the opposite side of the hill, and then use the momentum going first down the hill and then up to actually reach this. Yeah, and there are many examples, and we'll unfortunately will not be able to go much deeper into this than just some superficial descriptions and formalisms later in the course. But if you are interested in looking into this, you can visit David Silver's reinforcement learning course here on this YouTube link. So why is machine learning, so popular? Well, I mean, to be honest, I think it was popular also before 2010, but I think since then, especially due to deep learning, it's taken off exponentially. And there are a couple of reasons for that, and I wanted to show you that they really came all together in that time 10 years ago or so, even a little earlier. So we have more computing power. We either have cluster computers or even our desktop PCs are really powerful these days, or get even more powerful every year. And we have developed special hardware that accelerates vector and matrix operations on GPUs. And especially for deep learning, that's made huge difference. Data storage really has the cost for data storage is going down continuously. So the more data we need, the more money that costs. But this cost is going down. And that helped a lot storing and actually sharing a lot of data sets that then can be or serve as a reference data set, a reference task or a benchmark test for new models. And the community has taken up these things very well and shares a lot of stuff that they develop. Also the accessibility of not just data sets, but also all developments on this stack from APIs and libraries up to I don't know, ready-made notebooks for students to get into this topic is really remarkable. It's really unique here in the machine learning field. So let's start with some notation. let me switch to my pointer. The input to the model is usually named x. So this would be a vector. We'll see that in a second. And the model is usually called f. And f of x is y hat, the reconstruction or an estimation or an approximation of the labels y that were given in the supervised task. And we usually have samples or data points x as m-dimensional vectors, and we call those dimensions also features. So think of these could be pixels of the image, pixel values, pixel brightnesses, or it could also be something that somebody manually extracted from an image. So I don't know, if you have a dog on an image, this could be the size of the dog and the color and the furriness of its fur and all these properties that could be extracted either by a machine before or by human. X, so capital X here, the set of all those vectors is sometimes written as a matrix, so which each line corresponding to one of these vectors. The predictions on the output side, y hat, are also vectors, and these could correspond to, think of maybe the probability of the image being a dog, probability of the image being a cat, and all these things. But you are really free to define these output dimensions most of the time, or it needs to follow the problem description or the task description at hand. Y hat is usually not equal y, so we usually make a mistake, an error of the that cannot be minimized always to 0. So we have to live with this approximation. So as I said, f is the function we want to learn. Y is the label. Sometimes it's called target, given in the data set, and epsilon is the error. So let's go briefly over a couple of task categories. The first is classification. Here we do have any input, but the output y or y hat is not a continuous space. It is it has discrete states. Yeah. So for example, if we have an image of a dog and our task is to classify, the output of the model should say dog or cat or whatever other animal or whatever other classes we have, but those are distinct, discrete categories. Yeah, and obviously we wouldn't use a string as an output. We would use numerical values, but if the model now wouldn't produce a 2, which could be an index into an array saying, hey, this is a dog. If it would produce a 3, then this isn't a lower error in a way than if it would produce 10, right? Because these are categories and the space of answers isn't continuous. If we do have a continuous output space, for example, we have a cuteness regressor. Yeah? So given an image of a puppy, how cute is this, right? And the output could be between 0 and 1. Then if, for example, here for this input image, we had given 0.92 or so, there is an error that could be computed between the actual output and this label. And the closer you get to your label, the better, obviously, the model is. So really the question, especially in historical machine learning algorithms, the important question was, okay, what are the input features? So what are the properties of the data that will then be fed into or passed to the model. And you can think of the of the image as just a sequence of numbers. We could just put this right in there, but usually that hasn't been done. So let's look at an example that is given in this famous book here, Pattern Recognition. So think of a packaging plant that receives a shipload of fish and now wants to sort these fish into two distinct categories because most of them are salmon or sea bass. And the machine learning model now has to be trained on recordings that we have labeled. So we have a supervised problem, and let's now see what the problems really are when we want to do this. So think of the input not being the image itself, but rather a couple of features, attributes that a computer vision pipeline may have extracted for us. So for example, we could have measured the length, the body length, or maybe length times width or so to get an estimate of the weight of the fish. Or we could measure how light the color is, right? So some fish are rather dark and some are rather light. And if you look at how sea bass and salmon are distributed in this space, in this feature space, you see that most sea bass are brighter and most salmons are darker, but so those distributions overlap, and some sea bass are really light, and some salmons are really, sorry, the other way around. So some sea bass are really dark, and some salmon are really light. So let's have a look at how the data, our data set, really is distributed in this space. Space that's spanned by, let's say, we use 2 dimensions, the weight that we have measured or approximated, and this lightness. And so each of these data points here is really one fish, one image recording that was then post-processed by this image recognition pipeline or image processing pipeline, giving us 2 of these values, no? So one number for the weight and one number for the lightness. So each of these points is one measurement. And the color here shows you what the actual label is. Blue is again sea bass and green is salmon. Now, the task for the machine learning model that we want to train is to find a separation of these 2 classes. And we could, in the simplest case, think of a line separating the sea bass from the salmon, although we do make some mistakes, right? So these green crosses here, or these blue points here, are on the wrong side of this line. We could also think of more elaborate decision boundaries here. I think this was drawn by David freehand. And so what was his objective here? So obviously the green samples, the salmons here, are misclassified because they're on the wrong side of the border, but he was apparently giving more weight to the blue sea bass samples. And this is exactly a very important point. There is not just one model here. Given your task and given also your definition of what a good model is or what a bad model is, defines this decision boundary in the end. So to formalize a little bit more, we want to learn we want to approximate this data distribution or decision boundary from the training data, which is given by an optimization objective. And once we've learned this decision boundary or the distribution of the data, we can then classify a new, an unknown data point, or data point of an unknown class. Yeah? So in this case, the decision boundary given by the line here, a model that gives you a decision boundary that is linear, like this one here, would classify this yellow point as a sea bass, but would classify it as a salmon if we use another model that has this curved decision boundary. So one of the things that we need to discriminate here again is the optimization objective on the one hand. So that tells us in the process of learning the model, of optimizing the model, how to tune the model's parameters, or how to, if it's a non-parametric parametric model, how to change, how to improve the model's performance according to the data that we have given and obviously the objective. Once we've trained the model, we often have still some means to decide, especially in classification, decide how to take the model output and make a classification, a decision from this. For example, we could have trained a model that gives us the probability of the image being a dog or showing a dog, and then we could say, okay, if the probability that the model produces is above a certain threshold value, like 0.5 or so, we would classify the image as a dog and as no dog or something else if this threshold is not exceeded. And so you can think of the actual decision boundary here. Let's just reduce this to one dimension, to this one feature lightness, as still being somewhat flexible based on your cost functions. So, maybe it's helpful to think of something where different types of errors have different weights or should be weighted differently. So think of not a classifier that sorts sea bass and salmon, but would tell you your probability of having a certain disease or so. So let's say you having a disease would be this left part of the decision boundary, and not having the disease is the right part. Wrongly classifying you having the disease sometimes isn't as bad as wrongly saying you don't have the disease, right? Because if you go you live your life with the disease undetected, and then it gets worse and worse, and I don't know, maybe your probability of dying shoots up. So with having a way of tuning this parameter, or this actually it's a hyperparameter, this threshold in the example case gives you some power back to decide what kinds of errors are acceptable and which kinds of errors are not. Decision boundaries can, of course, live in the feature space, like we had, like 2 dimensions here. And like we said, there could be linear, but they could have, every possible form, really. And but the thing that I wanted you to realize is that even this very accurately looking line that kind of promises you very accurate classification results may not be the decision boundary that you want. Would you know why that is? So let's go back to the two-dimensional case in which we could have a very simple decision boundary, and you could imagine this moving towards more the sea bass side or more the salmon side to get less errors in misclassifying salmon or sea bass, respectively. But you can also think of more elaborate, like I said, decision boundaries here. And here on this slide, I wanted to ask you whether we always want to have a very precise model of the training data, or can you think of cases in which simpler decision boundaries like here would be beneficial, more beneficial? Or in other words, the question is, do we need to, do we require the model to learn the data that it has seen in training perfectly or not? Yeah? Or what advantage might we have if we consider less, let's say, powerful models? And I hope you kind of have an intuition of what the right answer is. The right answer is, well, we don't need a maximally powerful model that can perfectly represent the training data, because the training data is also an incomplete sample of the real problem. So we might see new data that differs, that deviates from the training data, and learning a model that tightly fits to our training data may overfit the training data, meaning that it gets worse with new data. So if a model is able to generalize, it's able to correctly predict new data. Yeah? And this is something that we will discuss later in a lecture that covers model validation. So how do we actually evaluate and quantify the performance of a model? And we, just to give you a little hint of what's happening in this lecture, we usually divide the data that we have in a portion of the data that is only there to train the model, and another portion of the data is only there to test the model. And if we see that the performance of a model is really high, but in the test case it's deteriorating, we know the model has overfitted the training data, and that's something that we don't like. Yeah, and there are ways to cope with the problem. So we really want the model to generalize to the real, underlying problem, to the new data that's coming in. So one of the questions that we can ask ourselves is, hey, so it's easy to discriminate between those 2 point clouds in 2D, right? Better than it was in 1D maybe. So what about 3D or 1,000 dimensions? And to be honest, you're right. Higher dimensions mean you got more space to have your decision boundary in there. Yeah, and hopefully you have chosen features, so dimensions of your space, that actually give you some information about what is salmon and what is sea bass. But, and that's called the curse of dimensionality, we do have problems with too many dimensions. And one of them is clearly that if you have more space, you need more data to actually give the model in the training process some information about what is good and what is bad, right? So where do we have to put the decision boundary? If it's too large of a space, you need exponentially many data points to actually fill the space. Yeah. So here in these three figures, in these plots, you see 10 random points along one dimension here, within 2 dimensions and 3 dimensions, and you can hopefully extrapolate to this to higher dimensions, that the space that you have is ever more sparsely populated, right? So, and this obviously is exponential, right? So the volume of a n-dimensional cube requires that many samples to be filled with the same kind of density that we require for a certain model to find a good solution. Yeah. And there are a couple of other problems with dimensionality. We will come to this a little later too. Now, for the remainder of this lecture, I'm going to present to you a very, very simple algorithm that's called KNN. I don't tell you what these letters stand for because they would kind of give away what it does. I wanted to ask you 2 questions. So let's say we have our C-base versus Salmon distribution in our training data, and this yellow point here is the new unknown data point. So how would you label this? So how would you classify this point? And I put it, of course, and I hope you kind of feel the same, in a spot in the data space that, I mean, intuitively, I would probably label it as a salmon, right, as a green cross. And here, this new point obviously more likely is a sea bass. But the question is, why? Yeah? Why would, and how would we judge based on the position in feature space? But what about this new point here? It's kind of, in that distribution here, it fits kind of to the tail of this distribution here of the sea bass and fits, almost in the center, to the center of this salmon distribution. So the question is, how can we, using this data, without any fancy model building now, classify this point? And the answer is, well, we use the algorithm KNN, which, and let me spell it out for you now, it means K nearest neighbors. So we have K many nearest neighbors that we compare, and whose label then determines the label of the new point. So let's say K is 5, and let me look closely. The yellow dot maybe has 3 blue neighbors and 2 green neighbors. So we would then classify it as the blue dot, so a sea bass. So let's define K nearest neighbor more formally. We have a training phase, like in any other machine learning algorithm. We have a training phase, although this one here is just storing all the data points that we have. So this includes, like I said, the inputs and the outputs. So the labels xi's are, in the 2-dimensional feature space like we had before, and the y's are either 1 or 0 for sea bass and salmon. Classifying a new sample now is just looking at the k closest points to x, and we call this set the neighborhood. Yeah, n subscript k of x is just a set of 5 vectors that are, like I said, the k closest points. Closest using some metric. Let's just think of the Euclidean distance here in the feature space, but really this could be any metric. The prediction y hat now is calculated as the average of the labels. So we take all of these 5 vectors in the neighborhood and take their label and then average this. So for I think I said 3 blue points, so 3 zeros and 2 ones, 2 green points, we would have a y hat of 2 divided by 5. The final classification could then, obtained by thresholding this value, and 2 divided by 5 is below 0.5, and so this would be classified as 0, so as a CBAS, if I'm remembering correctly. The choice now of K, of how many neighbors you actually ask, is really crucial for determining the decision boundaries. So let's have a look in this left plot here. The green background tells you, if the new point falls into this region, it will be classified as a salmon, and if it falls into one of these blue parts, it would the new point would be classified as a sea bass. And you see exactly what we mean by overfitting. So look, for example, to these blue islands here, or to these green islands. These areas correspond to the one sample that would be the nearest. Yeah, and so we expect that a classification based on just one nearest neighbor might be overfitting to the data and might not represent the entire underlying problem. So we usually take a little more neighbors. So David, my student David, used a K of 100 here, and you see that the decision boundary gets way smoother than we had it before. And of course, this question is just to reiterate what we called overfitting, and we have it here in the slides for you to remember that. Yeah, good. Well, I said that before. We usually use the training data to train the model, and then we take a bunch of data points that the training that the model has never seen in training. And we call this test data set, test set. And so let's say we look at the fraction of samples in the training set or in the test set that were correctly classified with a trained model, right? So after training, and in this case, we don't really have a training process because we just take the raw data set. We look at, okay, how does the training data perform and how does the test data perform using the training data? Yeah? And obviously, if we test every data point in the training set and look for the labels of its closest neighbor, then we obviously take the same point or the label of the same point and obviously have 100% accuracy here. So the number of samples that we correctly classify based on this is 100%, and that's clearly something that doesn't represent a realistic result, right? So if we'd had unseen data. And this accuracy drops really quickly down to, I don't know, 97% or so. And then the more neighbors we get, the smoother this decision boundary gets, and then the less good we perform. Yeah. And the same is true if we look at the 1NN for the new data. So we take a new data point and look into the training set for the closest point and take this label as a prediction. Then there's a huge gap of 6% or so. So 6% of the data points were wrongly classified. And the more we take, the more neighbors we take, the better this prediction gets, but then deteriorates over time. So the task for this problem then would be to determine the optimal k. So what would be the optimal k? Well, obviously some k here that um, uh, is close, so where both lines are close, but since both are decaying over this k here, this would be an optimal region. So let's look at the advantages and disadvantages of k and n. So first of all, it's pretty simple. You can implement this in really a couple lines of code. You don't really have to understand much, of the machine learning vocabulary yet, and so that's why this algorithm shows up here in the first lecture. KNN can be used for both classification and regression problems. So classification, like we just saw, you average your y hat, your labels into y hat, and then you can threshold it. You can also use it for like continuous outputs, and then you just average your labels, and then you have it. The good thing is that you do not have many hyperparameters, really. You will learn about models in which you have to decide for, I don't know, the number of layers of a network, the architecture, and all those things. Dozens of hyperparameters, and here you just have one. And also, this model is really non-parametric, so you don't have to assume certain structures. So, for example, remember you had your point cloud for the salmon and your other point cloud for the sea bass. You just take your data, right? So the data itself is a model of the problem, which is pretty accurate because this is exactly what you have, right? So the training data is exactly what you have, and then you just take the data. Modeling, however, isn't just simplifying the data, and you will see that later. It's also a way to generalize. Yeah. And also taking the complete set of data that you have also means that the decision process is really slow because you have to, worst cases, you have to scan through all your data points, which could be many. You can sort the data somehow, index it, and then somehow speed up the process, but still it's slow for big data sets. And also, if you have many features, many dimensions, your distance metric will get slower and slower. And also, KNN in high dimensional data spaces or feature spaces has been shown to be bad. So if you take more features, it gets first better, but then it drops off again, and you don't know in advance. You have to kind of test that for your given problem in your given data. Your distance metric may have to be tuned as well because your features may live in different scales. So let's say you have a size of 20 to 50 centimeters or so, right? So numeric values of 20 to 50. And the lightness could be from 0 to 1. So there's just very like numerically small distances in the second feature, but large numeric differences of the second one. And if you then compute the distance of one given data point to another data point, let's say Euclidean distance, then you end up with a distance that doesn't really care much about the differences in the lightness. So your task here is to scale or to normalize your data feature scales. And of course, you have to choose your K. We saw that on one of the previous slides. That means you just test different Ks and then take the best. Good. So that was the first lecture. I hope you enjoyed it. We will see each other on Monday for the first time to hopefully clear all your questions. We will soon upload your first assignment. Prepared to ask Max also your questions on Monday at 2 p.m. So that was me. Hope you enjoyed it. See you all on Monday. Bye.